Tēnā koutou katoa. Good evening, everyone. It's a pleasure to be here to talk to you today. So I'm going to be talking about galactic archaeology in Aotearoa's night sky. My name is Dr. C Clare Worley. I'm just going to tell you a little bit about myself before I get started. So I actually did my Bachelor of Science and PhD in Astronomy here at the University of Canterbury. So I've got some nice pictures here, start us off with some good pictures. Hagley Park, of course, and this is a view from Waitaha Mount John Observatory. After finishing that, I went to France and I was a postdoctoral fellow at the Observatoire de la Côte d'Azur in Nice. That was the view from the observatory down the south coast of France, the Mediterranean. So it's a pretty special place to do a postdoc. And that's the main big telescope or dome up on that particular foothill. After that, I went to Cambridge in the UK and was at the Institute of Astronomy there for a good long time, for quite a few years. Of course, that's a fairly iconic place with King's College there and one of the little telescopes on at the Institute. Then I found my way back here. So I am now a senior lecturer here at the University of Canterbury. So I've made my way all the way back to here to work a lot with the instruments at Mount John. So that's me. And then this is the field that I work in, galactic archaeology. We in the field like the way that sounds. It's quite a cool name, makes us think of Indiana Jones and space and all that sort of thing. So with galactic archaeology, we are trying to look for the fossil record of the formation and evolution history in the Milky Way, within the stars and the gas and the dust that make up the Milky Way. So this is why we quite like this image here, this idea of a spiral galaxy with a fossil record embedded in it. And in order to do that, we need to figure out as much information as possible for as many stars as possible in the Milky Way. So we're looking for information such as position, motions, stellar parameters such as how hot they are, how big they are, and what they're globally made of, and then also individual chemical abundances. So with all that type of information, we are trying to build a chemical kinematic multi-dimensional chart of the Milky Way. With that, we will look for substructures, populations, different groupings of objects within the Milky Way that we can help use to deconstruct how the Milky Way formed and evolved and compare it to our theories of galactic formation and evolution. So the game changer for my field and what has made it just have an incredible growth in the last decade or so is the Gaia satellite. You probably may have heard about it. It got launched in 2013. I think the more recent JWST, the Webb telescope, has kind of been the most in the news, and then there was Euclid as well not so long ago. So we really like our space telescopes, that's for sure. So Gaia is a European Space Agency mission, and its goal was to measure distances to 1 billion stars in the Milky Way. And that sounds like a lot, but it's actually only 1% of the stars in the Milky Way. There are 100 billion stars in the Milky Way. So we're making a good start. We've got a lot more to go, but we will keep going. And in fact, the latest data release for Gaia, data release 3, it actually had data for 1.8 billion stars in the Milky Way. So already almost doubled the amount. For most of those, we've got positions, parallax, proper motions, radial velocities. These are types of motion in the sky with which we can calculate orbits of these objects around the galaxy. And also a whole range of object classifications have come out of Gaia. So the amount of information we have to work with is just phenomenal. But at the heart of Gaia, in terms of measuring the distances, is actually quite a simple geometric principle, which is parallax. So this is a cartoon that illustrates it here. And you've probably learned similar geometric type things in school. So the idea with parallax is, so we've got the Earth orbiting around the Sun. And if we want to figure out the distance to this nearby star, what we do at this side of the orbit, we look at the star and we observe where it is located compared to these distant stars. So the position in June, actually it looks like this. The star is just slightly to the left of these distant stars. Then we truck around 6 months later, the other side of the sun. We take another picture of that nearby star and we see that it's actually moved, or has appeared to have moved, and is now to the right of all of those distant stars. So it hasn't actually moved, it's just its relative, our relative perspective of it has moved. And this apparent change in location is actually a change in angle. So what we're doing is we're measuring this angle here. We know this distance, it's just the diameter of the orbit of the Earth around the Sun. So with that measurement and that measurement, we can figure out the distance to the star. It's that simple. Well, it's not quite that simple, but that is what is at the heart of Gaia. The complication comes because Gaia is a little far away from the Earth. The Earth is moving around the Sun, but in an elliptic orbit, not a circular orbit. The Sun itself is also on the move. So there are many, many motions to take account of, which some very clever people have figured out and thus put into the calculations to get the parallax. I just want to do a little deviation, because this is just something fun I really like showing. Gaia isn't actually orbiting about the Earth. So we've got the Sun, we've got Earth, and we've got the Moon. So Gaia actually took a 1-month journey out to this stable gravitational point called L2. It's a stable gravitational point in the Earth-Sun system. So there's nothing there, but you can have something orbit around it, which is what Gaia does. So it's sitting out there, but it's not the only thing that's out there. In fact, so this is Gaia's orbit. It's quite complicated around this L2, but we've got JWST as well, and Euclid, all sitting out there. They don't crash into each other. It's pretty distant out there. But what the fun thing is that Gaia took a picture of JWST, which I just think is really cool. So this image here is a Gaia star field image. It's actually right down here is this little dot here, and that's actually JWST. It's quite extended because it's got these solar shields. And that's just a zoomed in version, and then another snap later on. So that was just a sidetrack, because just the idea of one space telescope taking a picture of another space telescope, I think it's kind of fun. So back to the topic. So this is the all-sky view of the Gaia Data Release 3. So Gaia is taking images and using it to measure positions and a whole host of other things, but it's doing it in several colours. So this is sort of a recomposition of the Gaia image, showing the disk of the Milky Way through here. We've got the bulge and all of the dust and the gas and this very turbulent structures that we see when we look at the Milky Way in our night sky. If you go kind of away from the city lights, we're pretty lucky in New Zealand. You can go not too far and you see the night sky. A lot of places just never see it. So what we see is those black smears in the night sky have got a huge amount of detail in the Gaia all-sky image. So for galactic archaeology, what we want to do is for every point of light that is a star, we want to figure out as much information as possible. And Gaia is a great start. It gives us a whole host of information and all the astrometric, the positions, the motion information that we need. But to do galactic archaeology properly, we need a lot more. But fortunately, we've got a lot of telescopes that we can use and have used and are using and will use. This is a selection of ground-based spectroscopic surveys that are all working and contributing towards galactic archaeology studies. So some early ones, RAVE and SDSS. Gaia ESO was the project I went to work on in Cambridge. And we were very specifically looking at the stellar populations of the Milky Way. Galar is a project that's still ongoing in Australia, so I've got a part in Galar, which is great to be back on this side of the world and working with them. We've got Gaia here, and these are some upcoming projects. We've foremost in the Mauna Kea Spectroscopic Explorer. the main thing I want to point out with these is that we're sort of really scaling up, particularly in terms of the number of fibres that each of these instruments will have available. So these are multi-object spectrographs, which means in a single shot we have n number of optical fibres to place on all the stars in our field for that telescope. So in particular, Rave is starting off with 150 fibres. That was a lot at that time. But now we're up to 5,000 fibres. The Mauna Kea Spectroscopic Explorer, possibly up to 4,000 fibres. So that's getting that number of stars in, say, 1 hour of observation. So we're not short of data is basically the main outcome from this slide. I know a lot of talks, science talks, you might get to the end and say, well, we need more data. I think we're good. We've got quite a lot heading our way. But what do we do with it? How do we put this all together? So Gaia is giving us the starting dimensions, if you like. So we have position information, that's our 2 dimensions. We add the 3rd dimension, so from parallax we get our distance. And then with velocity, so the proper motion is the transverse velocity, so the velocity across our line of sight, so that builds us up to 5 dimensions. And that's kind of is where Gaia gets us to, and then we need to add more, and that's when the ground-based spectroscopy comes in. So from a spectrum, we can get our radial velocities, that's the line of sight velocity. So between that and that, we can do all of the orbital information. Chemical abundances, and I'll talk a lot about those later on. And then based on all of those measurements, we can build even more, such as ages, masses, and a whole other range of measurements, which just increase the number of dimensions that we have available in this chart. So that's what we're trying to build up. But what are we trying to do with this all? So this is sort of my big data, big questions slide. These are all the questions that we're trying to tackle. And I've drawn these from the science cases of these 4 multi-object spectrograph projects that are coming up. Because we want to, now with the way the field is going, these spectrographs are being designed based on the science that we want to do. So we have to be very clear about what it is we're trying to tackle. So our questions and all to do with the formation and evolution of the Milky Way. How did the Milky Way galaxy and its components, so the halo, bulge and the disk, how did they assemble and evolve over time? Which components were formed in situ, so in place, and which are due to mergers, and how do we tell the difference between those? How did these different components interact during formation? Did they evolve together, or did one initiate the other? How much dark matter is there, and how lumpy is it? That was a key question in one of the in these science cases. What effect does stellar radial migration have? Because stars are born in one location in the galaxy, but they move around. And what impact does that have on our understanding? And also, for these stellar populations, what do their chemical signatures tell us? So these are some of the questions that we're trying to tackle, and all of them have sub-questions as well. But all of this towards figuring out how the Milky Way formed and evolved. But just first, a little refresher on the structure of the Milky Way. So this is quite a nice cartoon for just illustrating these different components I just mentioned. So the Milky Way is a spiral galaxy. So we have the bulge, so the centre of the Milky Way, full of stars and gas and dust. We have our spiral arms in the galactic disk. But all around this, we have the halo. So this is a spherical component of the Milky Way. It's fairly sparsely populated, but there are these stellar clusters called globular clusters, very dense stellar clusters, and this is also where apparently most of the dark matter resides. But I also want to zoom in, and that's why this picture is quite nice, to zoom in on the galactic disk, because even within that we've already identified subpopulations. So with the galactic disk, so if we look at it from a side-on view, we have the bulge here, and we have this first component, which is the thin disk. This is a young population. It's where most of the gas and the dust of the Milky Way resides. It's quite metal-rich. I'll talk about metallicity later on. And it's quite chemically, kinematically, it's very restricted to this thin layer. But then the other component is the thick disk, which is a lot more puffed up. It is an older stellar population, it's more metal poor, and kinematically it's got more vertical motion, so we call it that it's quite hot. So these are two quite distinct populations which we have found different evidence for. Now, I've put up this picture here of Jerry Gilmore. He was my boss at Cambridge. He and Reid actually predicted the existence of the thin disk back in 1983. And he's holding a little model of Gaia. It's not the actual satellite, it's just a model. Because he was the UK principal investigator for Gaia. But the key point is that he's a New Zealander. That's what I wanted to mention. So he was the first person when it was Canterbury College to get a PhD in astronomy. So he started off here and then he moved to the UK to become a professor in experimental philosophy. So, the last point I want to mention here. So this is the structure of the Milky Way that we've observed now. But how did the Milky Way form? So the favoured theory currently is that the Milky Way formed by a hierarchical bottom-up process, which means that it was the building up of successive mergers of smaller bodies. So we know that our galaxy didn't just form in situ; it's had mergers from other collections of stars and gas and dust infalling and building up the mass that is there. So what does this sort of look like? So if it's a hierarchical buildup of material, we would expect to see structures in the galaxy that are remnants of these infalling, merging bodies. So this is a simulation at different distances in the Milky Way halo, just showing how, so each colour is an infalling merging body, right? So it's just trying if the simulation is throwing these bodies in, and we're seeing where their stellar components end up. So we start from so this is at 10 kiloparsecs, so quite the inner halo. For reference, our solar system is at 8 kiloparsecs from the galactic centre. So you can see it's really quite well mixed up. There's probably been a lot of different events infalling, but they're really quite mixed up. And as we go to further distances, so this is more 10 to 30 kiloparsecs, 30 to 50 kiloparsecs, about here, that's where you're getting out to where the small Magellanic and the large Magellanic clouds are, but we're seeing a lot more structure, and then out to 120, 150 kiloparsecs, so really out beyond the disk that we see today. And we see just the simulation expects to see these bodies still very, very coherent. Not much stripping has happened at all. So this is structure that we expect to see about our galaxy and about galaxies like ours. But the problem was that we didn't see it. So that was troublesome. So this is an image of Andromeda, M31. And it'd be a typical image that we might expect to see. But with looking at M31 also being a spiral galaxy, we'd expect to see that structure happening around the galaxy, but we didn't. So it took the advent of large area CCD surveys. So CCDs are very sensitive detectors, and actually slightly smaller versions of what is in your cameras, your mobile phones. They're sort of a streamlined version of CCD cameras. And these are just really good at detecting light and capturing light. That's right, so we've got Andromeda here. And this is the image from a large area CCD survey where they could just stare at the sky and collect up all the photons that were there, because these structures are way fainter than the night sky. The night sky has a brightness of about 21 magnitudes. These things are between 30 and 23 magnitudes, because in astronomy a larger number means fainter. That's what we do. We like to invert our numbers. At any rate, once these really great detectors could come along, we could stare at the sky and actually start to see these structures. So this little image here, I've just stuck it on top, so it's our Andromeda here. So just to give you this idea of the scale and the extent that these structures are present. So what is this? This is evidence for the build-up of the spiral galaxy by the merging of successive events. So that's what I wanted to prove and show to you with that. And this is using CCD imaging, but now we are in the era of Gaia, and Gaia has given us similarly brightness and position information, but also motion information. And this was a discovery in the Gaia Data Release 1. So it is evidence of the merger of a massive dwarf galaxy with the Milky Way. So this is an artist's impression of the merger, just to give this idea of the size of the Milky Way compared to the infalling dwarf galaxy. So it's really, really big. It was more than 50 billion solar masses of stars, gas and dust were infall into the Milky Way. And they found it by looking at the kinematic information, comparing the circular motion of 7 million Gaia stars with their radial motion. So when we look at the spiral galaxy, the circular motion is the movement this way about the galactic center, so in the disk. And the radial motion is anything that's moving outward or inward radially, with no particular circular motion. So the disk of the Milky Way rotates at about 220 kilometers per second. So if we go into this graph, we see that here. So this ball here is all of the stars in the galactic disk. And they're all rotating at the same speed, and there's some random radial motion, but it's dominated by the circular motion. So it was this oblong feature here which they thought, what is this? This makes no sense. It's got no circular motion whatsoever, but it's got a range of radial motion. So this is the idea of what it's supposed to look like. We've got the Milky Way here, and then the yellow vectors are showing how this infalling material is slicing through the Milky Way. So that is the evidence of this major merger that was found in Gaia. So that's all very well and good for the outer reaches of the galaxy, but what about the inner galaxy? If you recall from that simulation, everything's pretty well mixed. It's not particularly easy to figure out which stars come from which body, because all of the dynamic evidence has been washed out. And this is when we start to use chemistry, and this is when galactic archaeology really gets going. I like this cartoon because it just nicely shows how stellar evolution enriches the Milky Way. So we start with the Big Bang, and it produced the primordial gas, which was predominantly hydrogen, some helium, and a little bit of lithium. So from this primordial gas, the population 3 stars formed. These were the first ever stars. So they formed and they evolved, and they're all pretty big, so they died as supernova. And the supernova are fairly cataclysmic events, and in the process of supernova, new elements were created. So these new elements were dumped into the interstellar medium. So we've got titanium, nitrogen, magnesium, all of these dumped into the interstellar medium, and new stars formed, the population 2 stars. But these would have the signatures of the supernova of the population type 3 stars. And then the same thing happens again. Some of these went supernova, some of them died as AGB stars, asymptotic giant branch stars. These have a more gentle stellar death. They sort of puff away their outer material, so it all gently drifts away. Planetary nebula are an example of the remnants of those, and then the core of the star would just die out. So this is how, and this process happens over and over again, and the stars that we see today show the chemical signatures of the populations that came before. And so we want to tie these signatures to particular events in the Milky Way. Another key point is that the metallicity, which is the global metal content for in my field for astronomy, a metal is everything that's not hydrogen, helium, or lithium. That's how we roll. It's all metals. That's what we call it. So the metallicity was pretty much zero back at the Big Bang because there weren't any, but it's slowly building up and up and up. So we call this regime metal rich, and back here metal poor. And that means metallicity is a proxy for time. So to first order, if it's metal poor, it's old. If it's metal rich, it's young. So we use this information, and as I said, we want to get every bit of information for all the stars we can see at this time. So we do this by chemical labeling, which is figuring out the chemical composition of all of the stars and saying, okay, that's their chemical composition. But then chemical tagging is identifying what the chemical signature is of a unique stellar population, and then looking for all of those stars that we've previously labelled to see if they've got that signature. And then we can say that they are of the same population, but we can find them all over the place because with the dynamics, they might have been scattered all over. So that's the idea that we're trying to use. So this is a little video, it's a bit dark, but just showing this chemical enrichment in terms of iron and the evolution of how the Milky Way might form. And I'll start it going. So red is dark matter. We'll start to see gas and stars and iron eventually. And it starts from the birth of the universe 13.7 billion years ago. And we first start to see clumps of dark matter bringing the gas together in streams. I don't know if you can see that. So the bluish sort of streams. And we start to see the clumping of material. And so this is the Milky Way forming in here. And as it evolves, so we start to see green. So that's the iron that's being produced. So the supernova idea. And then we're starting to see mergers of some of these other clumps of mass merging into the Milky Way. Now, in a little bit, when I see what the time is on it, sometime shortly, there we go, this last major merger. So potentially that merger that was found with Gaia, this is sort of simulating this last merger coming in, and so they never kind of fall straight into the Milky Way. They do a loop first and eventually infall. And that's how we start to see the spiral structure of the Milky Way. So I'm going to stop that there because it goes a bit further. So that was looking particularly at iron, but as I said, all the elements are formed from some process in stars. And I quite like this version of the periodic table because it shows the contribution to each element from different stages in stellar evolution. And we can see that some elements are bundled together as having come from similar contributions. So with each box, it's actually a little graph in the box. So you have the abundance, the amount of that element, and then the x-axis is actually time, or the metallicity like we talked about. And so as we get to the present, which is this side of each box, we see how much of each element has had a contribution from the particular sites of nucleosynthesis. So nucleosynthesis being where nuclei are synthesized and generated. So we have iron peak elements where we get something coming from the type 1a, type 2 and asymptotic giant branch stars. So you can see how one element has contributions from many different sites. And then we have pink contributions, so the neutron star mergers, they're more the heavier elements. So using this information and this idea of connecting events to the chemistry, this is how we're trying to unwind and unravel the Milky Way. So I'll go back to this picture just to remind ourselves what we're doing, which is we're trying to get as much information about all the stars in this picture as possible. And the first thing you have to do with stars is figure out their fundamental parameters, their temperature and their gravity. And this is from work I did for the Tauhere survey, which was a survey of 100,000 stars in the Milky Way. We had medium and high resolution spectra, so which gave us quite a range of information, complementary in order to be able to define our stellar populations. So in the Hertzsprung-Russell diagram, we have temperature, so the temperature of the star on the x-axis and the log g, so the surface gravity on the y-axis, and that goes to how big the star is. And then I've got this metallicity plot here. We use iron typically as metallicity, as a colour map. So here is the main sequence, and if I somewhere in this picture, it would be right about here. But we have a lot of sun, so this is a main sequence or dwarfs, and then the turn off and into the giant branch. What's neat about the giant branch is that you see the effect of metallicity, because the younger, more metal-rich stars are located here, and then as you go to older, more metal-poor populations, we see this rainbow effect of these different stripes. So in just a graph like this, we can already decode so much. So this was one survey. As I said, we've got lots of surveys going on and they're all generating stellar parameters. So this is just to give you a feel for how many stellar parameters we have available. But if we want to build these into one big chart, we kind of need to make sure that they're all saying the same thing, that they all agree. And so I looked at two of the surveys, Tauhere and Galactic. They had a nice overlap of 1,500 stars in common, selected from quite a few different types of stellar populations. This is the HR diagram, so Galactic is in pink, Tauhere is in blue, and then the cross match is in yellow. And you can see there are some areas which we haven't got any overlap, but where we are overlapping, it's looking really nice. Now I didn't do anything, I just plotted them, so seeing this was like, that's great. Already we're in good agreement. And then just for confirmation, Galactic values on the y-axis and Tauhere on the x-axis for temperature, gravity and metallicity, and again lying very nicely on the one-to-one. So this is, and by efforts by both teams to use reference stars that would ensure that their pipelines were returning as close to the truth values as possible, and by both teams working hard towards that, by just putting the data sets together, we're in good agreement. So feeling quite confident about our multi-dimensional chart. So with the parameters, we can then measure our chemical abundances. So this was from that same paper. And this is just showing the four sections of spectra that we analyse. And then all of the coloured lines are particular elements. So each spectral feature, so like this for example, which doesn't have a line, so that's typical, this one here, so this spectral feature corresponds to a particular element, and if we measure the strength of that spectral feature, then it goes to first order to the amount of that element that is in the star. So this, all of the coloured lines were spectral features that we measured in the survey. So we have an awful lot of the light elements, which is expected, and then the heavier elements is fewer lines, but enough lines for us to measure. So we ended up with a comprehensive chemical signature for all of the stars in the survey. And so we end up with industrial scale stellar abundances as well. And this is how we tend to look at chemical abundances. We look at the abundance on the y-axis against metallicity on the x-axis. And again, that's our progression through time, so older to younger. And the sun is at 0, if you want the reference point. So the zero metallicity is the sun, and 0 sodium abundance there. And so these just indicate which of these elements. Now I've grouped them like this because groups of elements do go together, and we can see that trend, similar morphologies for the alpha elements, this sort of around solar and then going up, and then say for the iron peak around solar but then decreasing. So in that way we can combine these elements and make them more powerful and kind of beat down our errors. But how do we use these? So we use these as chemical cosmic clocks, and this is a schematic of how we do this for the alpha elements. So that's this bunch here. So see, it's got at the 0 and then it goes up and is sort of in a plateau, right? So this is what that chemical clock looks like. So solar value, we have this plateau at more metal poor, and then a downward sloping line. So how does this work? So remember, this is metallicity, but this is time. So this is old to now, so the sun, and this is our alpha element. So we have oxygen to iron, so we're looking at the ratio of those two elements against iron. And here they're constant, which means the same amount of oxygen as iron is being produced. And that is because during this time, the main contribution to the material that the stars are forming from are type 2 supernovae, which produce alphas and iron. So they go together in a nice constant rate. But then something happens here which forces the line downwards all of a sudden. So that means that something is happening to change this ratio, and it's either that the oxygen is going down or the iron is going up. But we've always got supernova type 2 happening, so it must be something else happening that's producing more iron. And what it is supernova type 1a. So it's a different type of supernova that takes much longer to get to the point, but the system takes much longer to get to the point that it's going to explode. So these ones happen earlier, and then at a certain point, all of the systems that could explode as type 1 supernova start exploding, so they start kicking off, and this is the moment when they kick off and start dumping more iron into the interstellar medium, and so we see this ratio descend downwards. And that's that morphology that we showed before. So it's this idea of, for a particular stellar population, at what time in its history did the supernova type 1a kick off? And so that's a key moment that tells us about star formation rates and how that population evolved. So another method for us to allow us to do that. So this is taking that idea, so this is a global alpha abundance, and I was showing them just for a whole population of stars, but this, in a chemical cartography, is decomposing this whole population and thinking about it in terms of not just alpha against metallicity, but also R, which is the galactocentric radius, so the distance, so this set of stars here are between 3 and 5 kiloparsecs from the centre of the galaxy. And as we go along the panel here, we see that the bin in radius is changing. So here we're at the outer reaches of the galaxy. But not just that, we're also looking at Z, which is the distance above and below the galactic plane. So we're now looking at Z, we're moving upwards above the plane and below the plane. So here we're really in the centre of the galactic plane, and then we are moving outward, and this is more up to 2 kiloparsecs above the galactic plane. What can we see happening? So just globally, we can take a look at this and say, okay, well, we see this population in the disk, we're dominated by this population here, which is the thin disk, which I mentioned before. That's a metal-rich disk, and so it very much dominates in the plane of in the center of the plane of the galaxy through here. But as we move away from the center of the galaxy and in the inner region, we see this population popping in, and that's the thick disk population. So it's more metal poor and more chemically hot. So it extends further above the plane. What's interesting, though, is when we go to the outer regions of the galaxy, the thick disk disappears again. So in the images I've shown you, the thick disk, we've got it happening all the way out to here, but actually this is evidence that it really stops not much further out than the sun, which is at 8 kiloparsecs. So doing this type of chemical cartography allows us to see how these stellar populations are changing and moving in terms of regimes between the inner and the outer and in the plane and above and below the plane. So that is really a really nice study in galactic archaeology, bringing together chemistry and kinematics. So the next thing we want to do is we've got all of this data and all this chemical information, and we want to compare it to our models, our theories of how the galaxy has formed and evolved. So in making this comparison, our models need to account for the collapse of the gas and the metals into the stars, how the new stars, how many were formed and within these stars, and then the release of everything that's been generated within these stars back into the interstellar medium. So this again, you're getting very used to seeing these types of plots. I'm going to try to stick to these. So this is a different panel showing here is the abundance, and on this axis is the metallicity. So the same distributions we've been seeing, the black dots are the observations, but now we've got models on top. So all of these lines. So we start with the base model, which is showing contributions from supernova type 2, hypernova, and supernova type 1a. And then, so here Kobayashi has then added to that base model other contributions from AGB stars, other types of supernova as well. So this is a nice one to show. So the base model just really doesn't agree at all. But showing contributions from AGB and other sites of nucleosynthesis, it's matching better with the observations. So this is what we try to do, this end result of taking our data and comparing it. Now, a key person involved in the development of galactic chemical evolution was Beatrice Tinsley. So she was English born, but she grew up in New Plymouth, and hopefully you've heard about her. She's become more prominent in the New Zealand narrative. We've got a building named after her as well. So she studied at Canterbury University College back in the day, but then went on to the US and did a PhD at Texas, and then ended up being a professor of astronomy at Yale University. So she was instrumental in formulating galactic chemical evolution and its impact on our understanding of the universe. She was the first to devise a method to calculate star formation rates, which are key to understanding how fast a stellar population creates its stars and reaches its sort of steady state. And she was also the first person to consider that the chemical enrichment of galaxies were crucial for estimating the sizes and therefore the distances to galaxies. So the chemical enrichment will change the colour of a galaxy if it's more chemically enriched. But previously they thought if it was redder it was further away, but it could be redder due to chemical enrichment. So that will change the distance. And they use distances to estimate the acceleration of the universe and all of those key parameters. So to factor in those changes our understanding and estimate for the acceleration of the universe. Always go back to her papers because I always find something else interesting to build into this work. And I kind of wonder what she would make of all of this data that we now have available. So to sort of follow in her footsteps, one of my students, Kyle Butcher, he did his master's thesis with me last year and is doing his PhD now, took one of these tools that generates galactic chemical evolution and looked at the Gaia-Riso open cluster data set. So each point here represents one of the open clusters in Gaia-Riso. There were quite a few, and they reside in the inner and the outer galaxy, so this is galactocentric radius. And from this model, he derived the many parameters. This key one is the star formation rate peak. So when did, for a population, when did the most star formation happen? And what this is showing is this trend that in the inner galaxy, the peak happened a lot sooner than in the outer galaxy. So it confirms what was previously found. We were trying to test that this code actually works, but it indicates that the inner galaxy shows a more intense star formation period, while the outer galaxy has a more sustained, sort of prolonged star formation. What else was interesting here was this region, because it kind of shows the intense star formation seems to be the basis for some of the open clusters, but then another batch of open clusters seem to agree more with the outer galaxy. So our question is this a transition region between two regimes of galactic chemical evolution? And it happens to be located right where we are, which also makes you think, is this an observation bias? You know, it deserves further exploration. And so my main work here, I've finally gotten to it at the University of Canterbury, is to look at the solar neighbourhood, to look close in at the stars that are near and around us. So this is, if we were looking bird's eye view at the Milky Way galaxy, this is the sun that resides right in the middle here. So these big surveys that are happening are stretching out far and faint, trying to reach as far out into the galaxy as possible and building up these amazing data sets. But what they can't do, because they're on these really big telescopes, is they can't look at the nearby bright stars, because if you do that, you burn out the optics, and they don't like you doing that. But that's really important, all the stars that are near us, and potentially we're in this transition region, and stars that are nearby we can more easily observe and get more information about. So there are catalogues of nearby stars, so within 25 parsecs. So if you zoom in on this box here, the sun is right in the center, and that little red circle is the 25 parsec circle of the catalogue of nearby stars. We're very literal in how we name things as astronomers, catalogue of nearby stars. And then there's the Gaia catalogue of nearby stars, which is 100 parsecs only, so even tinier, but still on the order of tens of thousands of stars that we can observe. And so with this idea of observing the solar neighbourhood, we are well primed in Aotearoa, New Zealand, because our night sky is absolutely amazing. And this is an image, it's been the background for all my slides, from Aotearoa Mount John Observatory and the Milky Way just stretching above it. So all of these stars are available for us to observe from the 1 metre telescope at Mount John, and so that's what we have decided to do. We are going to look close and near and in fine detail to really figure out how and characterize all of the stars in our solar neighbourhood. So we're calling it the Solar Volume Survey. We've started with a sample of 1,000 stars. This is then just distributed in the sky. And everything with a magnitude brighter than V equal to 9, because that's a good limit for the instrument that we're using. So this is a picture of, that's the 1 metre dome just there on the mountain, and this is my team of students that are helping me do that. They love being down there. I think they'd live at Mount John if they could, so which is great. This is a video of the 1 metre. So the 1 metre telescope is what I'm using This is taken by our observatory technician, Fraser Gunn. So it's not actually daytime, it is nighttime, but he's just got a really cool camera. But you can just see the dome, sort of see the dome and the telescope moving. I'm using the Hercules spectrograph, so the high efficiency and resolution Canterbury University larger shell spectrograph. We made the acronym work hard. So if you were to go on a tour of Mount John, all you'll see actually is this vacuum tank, because Hercules is inside that. The vacuum makes it very, very stable. It's in a shell spectrograph, which means that we get a lot of wavelength, and we can do, this is very high resolution, and this is even higher resolution. So it's a wonderful instrument to use, and will allow us to investigate this great detail of the stars in the solar neighbourhood. So I sort of showed you the sample, and my students have got different tasks within that survey that they're doing. So I'm just going to show a few of the projects that my students are currently undertaking. Ethan is one of my master's students. He is looking at stars that host exoplanets. So he wants to try to understand if there is a difference in the chemistry between stars that host planets and stars that don't, as a way to find candidate host stars. So this is his sample here. He's got some that host, so he's gone to the NASA Exoplanet Archive, which tells you which stars have detected exoplanets. So he's got some with planets, some with protoplanetary disks. And with these are the parameters of the stars that are in the literature. So he's gone and observed some of those already, and this is an example spectrum from Hercules. And he's looking for particular elements, refractory elements and volatile elements, which are part of how a planet is formed. But he's looking in the star for these, and he's actually expecting to not see them. This is because if the protoplanetary disk about a star forms a planet, then all of that material goes into the planet. But if it doesn't, that protoplanetary disk is absorbed into the star, and so that star appears to have more of that material. So he's expecting that a host star won't have these elements, or so much will be depleted, and a star without planets will. So that's his investigation. So we'll see how that goes. Another of my master's students, Heather Sinclair Wentworth, she's looking at globular clusters. Now these are quite distant objects, so they're not near and close. They're very faint, and as part of her thesis, she is testing the limits of Hercules to see how faint we can go. So she's looking at globular clusters, and she's just, for this particular globular cluster, so this is the guide camera for the 1 metre, and she's placed the fibre just across the globular cluster, which has, you can sort of resolve some stars, but there's this background of smeared out faint stars. So we call this integrated light because we're collecting stars from a lot of different spectra. And this is her exploring that. The blue spectrum is from the very centre of the globular cluster, so she's managed to beat down the noise quite a lot, but as she moves outward, you can see a lot more noise in the green and the purple. So this is very sort of just testing to see what we can do in terms of getting data from the 1 metre. She also had a bit of luck with this particular globular cluster, NGC 6752, because it's got a really bright star there, which you can use as a guide star. So she did that. So she placed the guide on this star, and then she placed the fibre on this very, very faint 12.5 magnitude star. And if you recall, I said that kind of 9 was the limit that we could go for. But she had a go doing this, and she, after 16 spectra, 8 hours of observing, she got the black spectrum, you can see, so it's quite noisy through here, but the features are lining up very nicely with the same star that got observed on a 10 metre class telescope for about an hour. A lot less noise, but still seeing these same features. So yeah, I think this was a nice experiment then, that we know we can go fainter if we're prepared to spend 8 hours observing But if you're chasing the right star, then you definitely want to. And then finally, another master's student, Quinn Aiken-Davies, he's testing an alternate way on the Hercules spectrograph to look at spectral features not in terms of an element. I've been talking all the time about element abundances, but looking at the isotopes that contribute to that element. So this particular feature here, so the observed is the white, and then he's got synthetic spectra in the blue, and this feature here is a magnesium feature. Now magnesium has 3 stable isotopes, which tend to come kind of measured terrestrially in this ratio. What we want to do is try to understand, is this the ratio that each of these magnesium isotopes are contributing to this feature? Now he can play with the synthesis, and he can turn off 2 of the magnesium isotopes, and that's what he sort of did. You can make it out here. So he turned off magnesium 24 and 25, and then left these 2 features of magnesium 26. So we can do that. He's trying to prove that we can measure isotope abundances. Why do we want to do that? Well, magnesium can come from a variety of nucleosynthetic sites. It can come from supernova, black hole neutron star mergers, asymptotic giant branch stars. And so if we bundle them all together, magnesium comes from all of these. But then when we look at the individual isotopes, actually it's a bit of a mixture. For instance, S process produces magnesium 26 only, right? And for AGB stars, it doesn't produce magnesium 24 at all. So we can be trying to measure these different isotopes and using that to target which particular nucleosynthetic path it came from. So it just refines our understanding of where each isotope came from and this attributing to the different nucleosynthetic sites and thus events that happen in the evolution of the Milky Way. So it's really trying to push into even finer detail. I sort of lost track of time because we had the intermission, so I've got about 3 slides left, so I'll just keep going if everyone's all right with that. Because my last little bit is just to illustrate this idea of galactic archaeology on a stellar population that we all know very well in New Zealand, Matariki, or the Pleiades, as it's more known for the studies that I'm about to show. So Matariki, we see I'm told it's an asterism, so that this constellation of these 7 stars, but it's part of this larger open star cluster. So they're loosely gravitationally bound. It's formed in the disk and it's moving with the disk, and they will all disperse away eventually. These brighter stars are quite young, 100 million years old, and their lifespans are just on the order of a few 100 million years. For comparison, the Sun will have a 10 billion year lifespan, so we're about 5 billion through already. So we can look into Gaia and extract information about Matariki there. So this is the coordinates of Gaia, so Gaia of the Pleiades, so they're open cluster stars, and then I've just put the 7 Matariki stars here overlaid because they're actually too bright for Gaia. So it'll burn out their optics. So, but we get all the underlying stars. And it was initially thought there were 289 members of the Pleiades, but recently with Gaia it's increased to over 1,000. This is the colour magnitude diagram, so we see the brightest stars bright at the top, and then this is all the rest of the members extending down to very, very faint. So as I said, we've been looking around down to about 9th magnitude, but Heather's shown that we could actually maybe push down to here as well. So this is the type of study, or these are the type of stars that will end up in our survey, but a chemical tagging analysis has been done with the Galar survey on a set of open and globular clusters. So this is the idea of the chemical signature. We have these different elements, and for a particular cluster we see where the kind of the median value is, and then how the values are distributed by this kind of fun sort of distribution shown here. So this is the Pleiades here, so it's its particular chemical structure. What it found, and I don't know, you have to convince yourselves, the study reckoned that scandium, which is here, this blob, barium, this large one, and iron potentially show bimodal or two modes or a couple of different bumps in its distribution. Scandium maybe, I'm not completely convinced by the other ones, but that might indicate that this was two groups of stars that merged together. Another thing they found was quite a distance from the Pleiades, which has an extent of about 6 degrees in the sky. They identified two stars which appeared to have the chemical signature of the Pleiades but were much further away. So that was using these two techniques of galactic archaeology. So that's quite a tour. I think I've given you a lot of information and a lot of images. There was so much I wanted to show. So I hope you found it useful or interesting. So this field of galactic archaeology, you can tell there's a lot going on. It's a big data field because we're wanting this multi-dimensional chart of the Milky Way, and we are getting more and more data to help build that. The big surveys are really reaching far and faint, but here in Aotearoa we can do near and bright and get the fine detail, which actually will provide a good foundation towards these other surveys. And at the end of the day, honing our theories of galaxy formation and evolution. So thank you very much for listening, and if you've got some questions, please do ask. Thank you. Too much.
How does Gaia block out the brightest stars? Sorry.
Yeah, that's a good question. I think I didn't show it, but it's in its focal. So the question was, how does Gaia block out the brightest stars? So it's got a focal plane which has several instruments on it, and as the star, and it's actually taken a video of space because it's constantly scanning. I had to throw away some slides, there were already too many, but it's actually the first sort of video of space. And as the targets sort of scan across the detector, I think it's got some sort of filtering process at the start. Because a Gaia doesn't actually send down a continuous video, it's got pre-processing on board that identifies where there's an object and then cuts out that object from the surrounding black. Because if it was downloading the video, most of what you're downloading is just black because, star field. So I think it's got pre-filtering which detects when something's too bright, and they just discard it from the detector. So, yeah.
Thank you.
Hi, you said that that the Pleiades had stars show similar characteristics. Have they found any siblings for our sun?
Oh, solar-like stars. Yes, lots. Yes, that's a very what's the word? It's a key search that gets done pretty much for all the surveys, and we like to find solar-like stars because the sun is the star we know the most about. It's our reference star, and if we can find solar-like stars all over the galaxy, then we can make comparisons to that star, thinking that we've got, okay, it's enough like the sun. What are the differences, and are the differences due to the different galactic environments? So yeah, people, they're actually using solar twins was one way they did a confirmation of the distance to the Pleiades as well. Maybe not solar twins, but twin stars. So yes, we particularly the sun there are quite a few papers which have just a sample of solar-like stars.
Would they have actually come from the same stellar nursery, or just similar?
Just similar. So that would be where you do solar-like on some criteria. So mainly the temperature and the gravity and the metallicity. And then after that, you look at all the other chemical abundances, and they will vary. And that's when you try to figure out, and then you might look at distance to see if it's particularly close or if it's a bit more distant. So it's useful samples to find solar-like stars. Yeah. Yeah, so I think it was Beatrice Tinsley who was first thought that the chemical enrichment of galaxies has an impact on our estimates for the distance to those galaxies. Yes, because I think it was previously, light, the further away you are, the more red it looks, it's red shifted.
Because there's still a lot of unexplained discrepancies between
spectra. Yes, I mean, with the whole, all of the our cosmology of trying to understand how the universe is moving, expanding, and so these key things of knowing what exactly makes up the colour, or why a galaxy is a particular colour, and not necessarily due to it being far away and moving away from us, but also due to it's chemically enriched, so there are more red stars, so it looks redder. So that distinction was a correction to the estimated distances. But there are a lot more out there. Cosmology is a whole got a whole lot more things that they're trying to find. So yeah. Yeah, so because dark matter, I guess that simulation that I showed with the red dark matter and then the gas and the stars clumped into streams and threads, my understanding is they did that also because the dark matter itself is clumped as well. So it's got this presence. I'm not an expert on dark matter, but my understanding is that for baryonic matter that we see to clump, is doing so because the dark matter has as well. So when you're looking at the halo, say, of the Milky Way, and you're trying to detect dark matter, again, it might not just be a smooth, uniform distribution. It will have its clumpings as well. And you can try, one thing was looking at streams, so stellar streams. You can look for where the stellar stream is broken, and that might be evidence of a clump of dark matter or a lump of dark matter moving by and it's broken the stream, I think is one study some colleagues did. That's my understanding, but it's not my expertise, so it's very sort of, it's out there, it's in the halo. I'm looking at the inner parts of the Milky Way, so I can ignore it. Yeah. Oh, one more question, and then we'll finish up. Yeah. I think there's tea and coffee and biscuits waiting. I've been told that that's the new thing for the UC Connect. Oh, sorry. All of the survey data, or there are several different ways of detecting exoplanets with imaging and with spectroscopy, and of all the methods, I think that's definitely, in these big surveys, there are teams of people who are trying to use those methods for that particular data to detect exoplanets. I think what's really cool about all of this data is that many different fields use it for their own purposes, and what can be noise to me can be signalled for somebody else. So, I wouldn't. Gaia itself, so many other applications came out of it that they didn't envision at all. If it can be found, somebody will find it. That's probably a good point to end on. Thank you very much, everyone.